Hello everyone, my name is ILMA HUSSAIN. I am in BSc 6th semester regular and my roll number is 225040. My university roll number is 22103840101117 and my topic for presentation of advanced algebra is finite fields. So, what are finite fields? A field with finitely many elements is called a finite field. So, if a field has finitely means we can count the number of elements, then it is a finite field. It is denoted by F. In subscript we write Q, and Q denotes the element of the field. Finite field is also called Galois field, which is named after Évariste Galois, which is the founder of the Galois field in advanced algebra. So, what is a Galois field? For any prime integer p and for any positive integer n, a field containing p to the power n elements is called Galois field and is denoted by Gf. In bracket we write p to the power n. So, if there is any prime number p and it contains n elements, then it will be a Galois field. Here we can see Gf stands for Galois field. So the example of a Galois field is a ring Gf p to the power n is a finite field of characteristic p. The prime number p is also called characteristics, where p is a prime number. So next is order of finite field. The number of elements of a finite field is called order of finite field. So the number of the elements in a finite field F subscript Q is called order of finite field. A finite field order Q, the order Q of a finite field exists if and only if this equation is satisfied. The equation is Q is equals to p to the power k, where p is a prime number and k is a positive integer. Now we will see some properties of finite field. First property is the characteristic of finite field is necessarily non-zero, but the converse is not true. So the characteristic of a finite field is a non-zero or a prime number. Property 2 is order of a finite field of characteristic p means if there is a finite field whose characteristic is p is of form p to the power n, that is जो order होगा it will be of form p to the power n, where p will be a prime number and n will be a positive integer. Property number 3 is every element of a finite field with p to the power n elements satisfies the equation. This equation it will satisfy, and the equation is x p to the power n is equals to x. So if a finite field follows this equation or satisfied this equation, then it will be a finite field with p to the power n elements. Property 4 is if finite field f has p to the power n elements, then f is the splitting field of the polynomial fx is equals to x p to the power n minus x. So if there is a polynomial fx, this is the polynomial fx, and we have to find the splitting field, then it will also be a finite field which has pn elements. Next is existence and uniqueness theorem in finite fields. For every prime integer p and positive integer n, there exists a finite field p to the power with p to the power n elements, and this is unique apart from isomorphism. So apart from isomorphism, we have p to the power n elements in a finite field. So in a finite field there will be two things, that is existence and uniqueness. Uniqueness can be explained by isomorphism, and existence can be explained by the number of elements, that is p to the power n. Here it should be noted that finite field having same number of elements are isomorphic. So if two finite fields have same number of elements, then it will be isomorphic. Now multiplicative structure of finite field. It can be explained by a theorem. Theorem states that the multiplicative group of a finite field is cyclic, and the converse is also true. If there is a cyclic group, then there will be a finite field with its multiplicative group. Next is primitive elements. Let f be a finite field. A generator of f dash, that f dash's multiplicative group is called primitive element. So every finite field has a primitive element and it might be the multiplicative group. It should be noted multiplicative group of Galois field is cyclic. We have already seen this by multiplicative structure of finite field, that finite field is cyclic. So here we can also see by primitive elements that multiplicative group of Galois field is cyclic. Second, every finite field contains at least one primitive element. So in every finite field there must be one primitive element or multiplicative group. So now theorem states that for each positive integer n there exists an irreducible polynomial fx over degree n over ip. Second theorem is, if K is a subfield of a Galois field, if there is a Galois field GFP to the power n and K is the subfield of this Galois field, then there exists an integer m such that K contains p to the power n elements such that m upon n. So if there is a subfield K of Galois field and Galois field have p to the power n elements, then the subfield K will have p to the power n elements such that m upon n is satisfied. Lastly, polynomial over finite field. A polynomial fx belonging to capital K x is called irreducible if it cannot be expressed as a product of polynomial of lower degree over finite field K. That is, ux upon fx will either have ux is equals to constant or ux is equals to fx. So if we solve this and we get ux is equals to constant or ux is equals to fx, then we can say that it is a irreducible polynomial of a finite field. That means fx is a irreducible polynomial of a finite field. If not, then fx will be a reducible polynomial of finite field. Thank you.